Hello everyone, good evening.
Good evening, ma'am.
Good evening, ma'am.
So, how was quiz 2? How was quiz 2 for you?
Moderate.
Moderate. Anyone else?
Actually, this kind of average, this I mean, the problem with me is like time is one constant, and even though I understand the concept, but when all the problems are different, not able to uniformly apply the learning in the problem statement. Need to
Uh,
practice.
I think very few problems would have been different. Most of them you would have seen in some way. Huh?
Maybe I did not practice all the pattern. Like I normally don't join the PYQ. Only that whatever the live session problem statements are done, I follow
Yeah.
only those.
Then it would have been a little difficult because when you go for exam, I think practicing more different kind of problems always helps. Um, okay, so I think we still have time for the end term if you haven't been able to do well in quiz 2. So you should start, I think, you should start studying for end term.
Intermeters will be 60%, right? If I
Yeah, it's
remember.
more like going to be 50-50, like roughly 50% will come from week 1 to 8, and 50% will come from the number of questions only. So,
Okay, okay.
yeah. Mm, yeah, you can like start revising all the weeks. And I think week 9 to 12 might be a little different and difficult. So study it properly. Okay, let's get started with week 9. So have you been able
Hello, ma'am.
um, yeah,
Yes, ma'am. Before starting, I have a doubt in one of the question
mm,
in quiz 2.
okay.
Uh, can you, that was, is the last question, 15th question.
Mm, I think it's knife based problem.
Yes, ma'am.
Okay.
Ma'am,
Very big stuff.
actually, if how, uh, because I'm, for that question, I have not got the marks because I have chosen a wrong answer. But why the correct answer is there? Can you explain that question?
Okay. Um, do you have the paper with you?
Yes, ma'am.
Can you present?
Oh, okay, ma'am. Yes, ma'am.
Hello, ma'am.
Yes, Kevin.
Ma'am, how are the results like in general?
Um, Results are okay, I would say.
Okay.
Um, okay, I think now go to next one.
Yes, ma'am. This is the question.
Oh, this is the question talking about, not the my base.
Oh, sorry. Yes, ma'am.
Okay. So, so you have the data set given to you, right? And what is known as that xi is in R and y also is also in R. Uh, Let W star with the least square solution, which is the following will fold. So, what do you know about the least square solution? What criteria should it satisfy?
Ma'am, it is that for uh, least square, we have to minimize that uh, y minus the wxi.
Yeah, so we minimize this mean square, right? So 1 upon
Yes.
n sub over wi minus w transpose xi. Um, whole square is what we minimize. Right?
Yes, ma'am.
That's correct. So how do you solve for it? If W star is the least square solution, then what should hold? What do you do? Like, see, you have the MSC with you, you have the general state, I mean, function with you, objective function. Now, if you have to find, if we are saying W star is the least square solution, then how did you reach to that conclusion? Right? So, what will you do?
Act-
You will
uh,
differentiate, no?
uh, yes, for by differentiating, uh, for that we get our W star,
Yeah.
that is X transpose X inverse XY.
So, you will differentiate with respect to W and you will equate that to zero. That's exactly the option says. Nothing much.
Okay, ma'am.
Are you able to understand?
No, ma'am, actually.
No. So can you write? So see Wi minus
Ma'am,
W transpose Xi.
ma'am, I am unable to write because I am stopping scaring, showing the screen. Can you? Because I have no.
Okay, okay. I will write. You showed me the question. You can stop presenting.
Yes, ma'am.
Hmm. So what is your objective function? That's right, LW. It is 1 upon n, I varying
Summation.
from n to n, yi minus W transpose Xi whole square.
Yes, ma'am.
What we are saying, W star is the solution, right? So how do
Yes,
we
ma'am.
reach to that solution? You differentiate LW, right,
Yes, ma'am.
with respect to W.
W.
Hmm? What will you get? 2 times Wi minus W transpose Xi. And then you have this W like Xi with you, right? Because you are differentiating
Excellent.
with respect to W. Okay.
Yes.
So I think we, okay.
Okay. Okay. Yes. Yes, ma'am. I got.
Got it. But now
Yes,
it's
ma'am.
Xi is in just an hour, so this doesn't make sense. So you'll just, sorry, this is Xi. So you'll just substitute this, so this should be 0 is what it should satisfy. So that's why the answer is sum over W star Xi minus YI Xi.
Yeah. Yeah, ma'am.
Okay.
Oh, yes, ma'am. Okay.
Hmm.
So the error vector should be perpendicular to the feature space, right?
Yeah.
Ma'am, one thing more I have to ask, not related to the question. Will there be any bonus activity and or question in MLT for our T score, final T score?
So okay. So in MLT, you have the bonus if you do the programming assignment. If you submit the programming assignment, so when you started the course, this is something that is already given to you on the portal. So programming assignment is a bonus component in this course. If you do it and submit it on time, you get some bonus points. So that's the only bonus component you have.
Okay, ma'am. And ma'am, for that I have solving this programming assignment. It was told that we have a 40% if the overall marks is above 40%. So this 40% includes all the 12 weeks or 11 week or 10 weeks, that sort of.
Sorry, what 40%?
uh, we have got that we have got in our course portal that our grading our bonus marks will be only awarded if average of all assignment will be
Okay, okay.
greater than will be greater
Yeah,
than
like, okay,
40%.
okay. So bonus is only applicable if you pass the course, basically. If you don't pass the course, then bonus does not make sense. Okay. So
Yes, ma'am.
yeah.
No, I was asking that it is written that the bonus 3 marks awarded for programming assignment submission if average of all assignment will be greater than equal to 40%. So for that, want to ask that it is for above 40% for all 12 weeks, or it will be 11 weeks or 10 weeks only programming assignment.
It should have been mentioned.
No, ma'am, there is no such mention.
Oh,
It is
okay.
only
Then
mentioning
it should
all over.
be all the weeks. Not mentioned, it means all the weeks.
So in our 12th week also we will get a programming assignment. No, ma'am.
So in week 11, week 12, we don't have programming assignments. Programming assignments are only till week
Oh,
10, which ends at SPM. Okay. So
oh,
whatever assignments are there, if you score that much marks, you will get the bonus. Don't worry about the bonus and all right now. Well, if whatever the criteria are for bonus, if you satisfy it, you will get the marks. Okay.
yes,
So
yes, ma'am.
if you do the mock, if you do the programming assignment, whatever, and if you satisfy the criteria for getting the bonus, you will get the marks.
Yes, ma'am. Thank you, ma'am.
Okay, all right. Okay, let's get started now. So we are starting with a new algorithm in week 9, and that is called perceptron. Um, so not just perceptron, actually, we are going to look at two classification techniques. So one is perceptron, and the other is logistic regression. So has anyone watched the lectures from week 10?
Week 10.
Sorry,
Ma'am,
sorry,
week
week 9.
9, no.
Week 9, week 9.
Yes, ma'am.
No,
Yeah,
Yes, ma'am.
okay, that's okay. So if I ask something, please uh, give the answer, okay? So,
Okay, ma'am.
so in perceptron algorithm, what is like we have like just before we start. So there is one assumption that we have made on the data set, right? And that assumption is linear separability assumption. Okay, so it means there is some underlying W in the data set which is separating my data point into two classes. Okay, so we are assuming such there is some W and it linearly separates my data set. So uh, when we are saying my data set is linearly separable, means how should it look like? So suppose all the positive points are on this side and all the negative points are on this side. So from here I can see that maybe there is this W which which linearly separates my data set into the positive and negative, right? But what would have happened if there was some W, sorry, some data point, maybe there's a data point here, which is the positive label. Yeah. So can we say that there is some W which is linearly separating my data set in that case? No, we cannot say that, right? Because there won't exist any W that would have generated this kind of data set. So this doesn't come under my linear separability assumption. So again, this is, let's make it minus. So let's say this is this is a data set that we have, and there is this W that linearly separates it. So like if we have to write it more formally, like what this linear separability means. So we'll say that there is some W, so that is there exists some W which belongs to RD such that sign of W transpose Xi should be equal to Yi. So let's call these to be +1 and call these labels as -1. Okay. This for all I from 1 to n. Okay. So what is the perceptron algorithm looks like? So it's a very simple algorithm in general. So what we do is first we assume that like step 1 if we have to write. So first you initialize your weight vector. Okay. So we'll first start with a weight vector W0. So this is a set of this is a vector which takes all the value as 0, right? So W0 will still be in RD. So first initialize the weight vector to be 0. Then what we will do is, and then the step 2, we say until you converge. So until convergence, we will follow few things, right? So we have a data set with us, which is x1 y1, x2 y2, so on till xn yn. Okay. So we pick any data point. So let's say I pick xi comma yi. Okay. So I pick xi comma yi. Now what we do check is, we check whether the sign of W transpose xi is equal to yi. Okay. So if this holds, so if my sign of W transpose xi is equal to yi, then we don't do anything. Okay. So we'll just try do nothing, because there has been no error in that case. So whatever the data point we pick, the sign of W transpose xi exactly matches with yi, so we'll do nothing. But in case it doesn't match, right? So if sign of W transpose xi is not equal to yi, then what do? Then we do the update. And what is the update? So we are looking at the weight vector at any point t. So at the t plus 1th iteration, I will update my weight as wt plus my xi. Okay. So we're just adding this. So whatever the weight vector we have at the tth iteration, we are adding this xi to that. That's all. So this is my update rule for the perceptron. Okay. So it's simple. It's a very simple algorithm. Now we can see that only like if and what we do is, like, until you reach to a point when there is no such data point where the sign doesn't match, then we can say that we have reached the convergence. Okay. So actually, like, when we talk about the perceptron algorithm, like it has been theoretically proved as well that this perceptron algorithm that we have discussed, the update rule that we saw, and the way perceptron works. So this algorithm, perceptron algorithm, always converges. This always converges. So this has been theoretically proved as well. Now to see, like, this update that we are doing, that is, if there was a mistake, then we are making the update as wt plus 1 to be wt plus xi, right? If there was a mistake, we were doing this. So how does this update rule make sure that like doing this update, we are actually doing the right thing? Like if my actual label was positive but it predicted to be negative, then doing this update should try to move that point. I mean, should try to give us a weight which is which should go more towards the positive side, right? So something should get added to it. So again, like if we are doing this update when there was a mistake, okay. So there are two possibilities in which we can make a mistake. So one possibility is, so mistake one we can say, so type 1 mistake we can say. So type 1 mistake is when, so what are the possibilities that uh, the true label is actually 1, but what we have predicted is -1. Okay. And the second type of error that we can get is type 2 is the true label. So like there is no any, I mean, type 1, type 2, I have just written for reference. I mean, there is no such rule that says type 1 should be this and type 2 should be this. All right. Like just to not be confused with hypothesis testing. So the true label, the mistake of type 2, maybe the true label, let's say, is -1 and the predicted label is +1. Okay. So these are the two possibilities where the mistake would happen. Now, if the predicted label is -1, then your like what should the sign of W transpose Xi be?
-1.
Negative.
Negative, right? So I can write that this is less than 0. Yeah. So okay. Instead of doing this, let's proceed like this. So okay. So if the true label is +1 and the predicted label is -1, then we are doing the update, which is WT +1 transpose Xi. Okay. And this should be WT plus Xi by I transpose Xi. So we have done nothing. We have just taken the update rule, which is WT +1 is equal to WT plus Xi by I. And we are seeing like how does the dot product of this looks like. Okay. So like now if we solve for this, what do we get? We get WT transpose Xi plus Yi transpose, since but Yi is a just a real number, so this is going to be Yi times Xi transpose Xi. Okay, and Xi transpose Xi, we know this can be written as, so this is going to be WT transpose Xi plus Yi. This is nothing but norm L to norm of Xi. Okay. But now, see, since the predicted label is -1, this term would have been negative, right? This is okay. All right. So if this WT transpose Xi, like if the predicted label is -1, this should have been negative, and this term, since Ya is the true label is 1, um, this is just a positive number because this is going to be norm of Xi square. Okay, so this is always going to be greater than 0. So what we are doing is we are adding some negative quantity to this to this Wi Xi square, norm square. Okay. So if we are adding some negative quantity, it means we are moving towards the negative side, right? It is slowly going to move in the like it is. We can say that it is moving in the right direction, right? Similarly, if we have to look for this, when the predicted label is 1 and the true label is -1, then in that case, if we solve for this, I won't write in here. So what we will have is that WT transpose XI plus YI XI norm square. So if the predicted label is +1, this would have been positive, and since the true label is negative and this term is always going to be positive, this whole thing would have been negative, less than 0. This is fine. So making sure that where the true label was -1 and the predicted label was +1, when we did this update, because of this mistake, we can see that we are like subtracting some positive quantity from my WT transpose Xi, right? So we'll slowly move to the negative side, and that actually aligns with this true label being negative. Okay, so in both the cases, what we saw is that doing this update, we are making sure that we are moving in the right direction. So we are pushing this W in the right direction by doing this update. Okay, so from here we can say that this update rule actually works. But something that can go wrong here is that there must be some point where which would have been classified as correct with initial W, maybe with W1, some point would have been classified correct. And when we did, maybe there was some point for which the my algorithm was making a mistake. So we did the update and we got a W2. So it is quite possible that now this W2 is making more number of mistakes than my W1. Okay, so like so we have to be a little careful on when we talk about the convergence for the perceptron. So one thing that from where we started, uh like just saying that, just assuming that the data set is linearly separable, that is, it holds this condition, that is, there exists some W such that the sign of W transpose Xi is equal to Yi. Uh, just this much is not sufficient when we talk about the convergence for the perceptron algorithm. So there is some additional assumption that we are going to make, and that assumption we are going to call it as linear separability assumption. With gamma margin. So what does it mean by saying that the data set is linearly separable, but with some margin gamma? So, if we have to write it mathematically, so what we are saying is that if D is a data set which looks like Xi, Yi pair, where I is varying from 1 to n, if this is my data set, then we are saying this data set is linearly separable. So let's write it as linearly separable with gamma margin. If you have some W star, so if you have some W star which is in RD, such that this holds, which is W star transpose XI should be greater than or equal to gamma for all I and gamma positive. So if this holds, we can say that my data set is linearly separable with gamma margin. Okay. So if like let's see how it should look like. So maybe this side we have all the positives. This side we have all the negatives. So this is my W, W star, and this is in boundary. So what we are saying is that there is some margin gamma. So it is not just linearly separable. There is some margin which actually some margin between this in boundary linear classifier and from where the data points start. Okay, so there is some gamma which there is some W star which linearly separates my data set with the margin gamma. Right. What here is it clear?
Hello, ma'am.
Yes, tell me.
Ma'am, in this, we are selecting this gamma line.
Not gamma.
Actually, uh,
Tell me.
okay, selecting, ma'am, this gamma that is W star Xi, and the first W star which we are choosing is of all zeros.
Hmm.
Is okay, ma'am. And the Yi which we are selecting is the first nearest Yi for positive side and nearest Yi for negative side. Is it or any Xi or average of sorry Yi or average of all Yi?
What is about YI you are talking about? So your YI is only take two values, right? You have two labels. So YI can either be 1 plus 1 or your YI can be minus 1, right? So if we are saying this, what is this going to mean? That my W star transpose Xi and YI is plus 1. So this is greater than equal to gamma. And if YI is minus 1, it means this is W star transpose Xi of, so this will be minus greater than equal to gamma. So this can be written as W star transpose Xi less than equal to minus gamma. Right?
Okay, ma'am.
So
How we are deciding the gamma line equation that
how are we
because
deciding this gamma margin?
yes, ma'am.
Ah, so okay. So this is something that it's not that we are deciding this. So like you have the data set with you, right? So from there, maybe there is some margin, like with which, uh, like my data, this W star is separating my data set, and there is the some distance is there. I mean some margin is there. You say, I mean it shouldn't be like if this is my W and this is my classifier, linear classifier, or this in boundary. So it shouldn't be like there are points which are exactly falling on this line, right? On this distant boundary. It shouldn't be that case. Okay. Uh, like we have also seen that if there are cases like that where your data point exactly falls on the distant boundary, then we have seen there might be a problem with convergence. Okay. But if there is some gap, okay, if there is some gap in the data set, some gap between the classifier and the data point, then this holds. Okay, so we are just assuming that this should this property should satisfy. This is an assumption we are making. See, this is
Ma'am,
an assumption.
may I interrupt
प्लीज
point
एक
out here?
नोटेशन समझा दो मैम, ये वेयर ऑल आई क्या है ये?
Hmm. What?
मैम दिस वेयर ऑल आई, व्हाट इज दैट नोटेशन?
Where all
For
I
all, for all I.
for all. That is for all.
Ma'am, can I ask one doubt? I
Yes.
actually did not understand what is the necessity of gamma. Initially, If the sign is different, then we decided to move to t plus 1. Okay.
Hmm.
And in t plus 1, there are two types of error. That is what you are talking about.
Hmm.
And after that, that we get W transpose Xi plus Yi norm of Xi is Xi.
Hmm.
So the second part is becoming negative,
Hmm.
but first part is still greater than 0. Uh, Correct? Am I right? So why we are needing this? So is it not the second part is negative
You're
and
talking about this one, no?
yeah, this line where you wrote uh, WT transpose XI plus YI. This is what one part is less than 0 and other part is greater than 0.
Hmm. So
So
here, see, um, what we predicted is -1, but what the label should have been is +1. Okay. So since we have predicted a -1, this term is going to be less than 0, right? And this term is going to be greater than 0. So since this term is always greater than 0, because this term is positive and my y is also +1, so this is always going to be positive, greater than 0. And in some positive quantity, we are adding a negative quantity, which is this term. Okay. So over the time, like it is actually from the positive side. If this is, let's say, the positive side,
but
then
ma'am,
you
in
are
the recorded
actually
session,
moving in the right direction, right?
so in the recorded session, professor showed that the first is greater than 0, that WT
How?
transpose XI greater than 0,
How
and
did it come?
WI is, no, I think that is how it is, or maybe
Yeah,
I'm,
yeah, this one you're talking about. And I think this was done first in the lecture. Yeah.
correct.
So WT transpose XI, this will be greater than equal to 0. And XI square is always positive, right? Because it's a distance. But true label is -1, which is, so this second term, which is yi norm of xi square, this is going to be less than 0. Okay. So this term is always negative. This term, so this term is always negative, maybe some point here, let's say. But now to this negative term, you are adding a positive term. So you will eventually move in the right direction. And the true label, sorry, wait. Um, this is less than 0, and this is greater than equal to 0, right? So, oh, I think I've written it wrong. True label is -1, predicted to be +1. So, W transpose Xi plus YI. No, this is fine. So, this term, which is true label is -1. So, this is -1 plus this is a positive term. So, this overall thing is going to be negative. And in some negative quantity, you are adding a positive term.
Actually, ma'am, since xi will be negative, so first quantity will be less than 0, and since yi actual value is also negative.
No, look, let me redo this. I think I was a
Yes,
fraction.
ma'am.
Let
Can
let
I
me,
we
think
take a variable also?
yeah, let
It will
me
be more clear.
rewrite this. Okay. So what we are saying is that prediction, prediction is 1, but the true label is -1. Okay. So true label is minus, saying that true label is -1, it means my yi is -1. And saying that the prediction is 1, it means my W transpose Xi has to be greater than equal to 0 this time. So
The
due
Yes.
to
sign
the
of
error
it.
that it is making, then my WT plus 1 transpose Xi, which is WT plus xi yi transpose xi. This is going to be wt transpose xi plus yi transpose xi. So this is going to give us wt transpose xi plus yi xi square. This fine. Now xi square, this is always going to be positive, and yi's are, they are -1. So this is negative. So this overall, this term is going to be negative. Fine. This overall term is negative, and if we look here, which is wt transpose xi, this has to be greater than 0. Okay. So this is positive,
It will
and
get pushed to the origin, right? What you told earlier. Is it correct?
it will go closer to origin.
Because this overall
Actually, W transpose Xi is positive, and since our through level is -1, so by subtracting, we are pulling it towards minus negative portion. That's what out of my thing.
so actually the overall value is the left hand value is positive, right hand value is negative. So if we add
Right.
up, it will
Yeah,
get
yeah.
pushed towards the origin.
Right. So this is a positive term. This is a positive term. This is very 0. So this is a positive term, but now we are adding some negative quantity to it. So it will eventually move to this direction, right? This is okay?
Yes, right. That is what I was saying actually.
Yeah. So this was my prediction. That is wt transpose xi has to be greater than equal to 0. So if this is the prediction and it is positive, then adding a negative quantity to it. So this is a positive and we are adding a negative quantity. So you're subtracting something from this quantity, right? So it will eventually move this W to the right direction. Is okay?
Yeah, right direction in a sense. You are saying it need to be -1, so it will move towards that.
Yes, because the true label is -1. So as you keep progressing through different iterations, you will this algorithm will push W to the right direction.
Got it, ma'am.
So,
So slowly it will converge to -1.
yes. Okay. So there is this one example that is done in the lecture. Um, how many of you have seen that example?
Uh, yes, ma'am. That was clear. But since uh, can you scroll up, ma'am?
Scroll up, yeah. Hmm. Yeah.
Yes, ma'am. Yes. This is the area that W star Xi yi should be greater than gamma.
Hmm.
Why we are comparing it with this?
No, no, we are not comparing anything, right? So what we are saying is that instead of just assuming this linear separable, that we just said is linearly separable, what we are now adding is that it's not just linearly separable, it is linearly separable with some gamma margin.
And
Okay.
That
this
gamma,
gamma margin.
sorry.
Okay.
So
That
how does
gamma,
yeah.
the gamma margin we have to keep because it is close to it, but it is not exactly -1 or +1. It needs to have some space. Is this the reason that the
It's
gamma
not,
margin is
yeah,
required?
it may not be, this gamma may not be +1 or -1. That's true. Okay?
Correct. So we are leaving the margin because we are not getting the
We
exact
don't
value.
want, yeah, we don't want my data set to be lying exactly on the decision boundary.
Okay,
So
okay.
that's why this, you will see the strict condition on gamma is there. So gamma has to be positive. So if you look at this line should be that this should have a set of all x such that my W star transpose x should be equal to gamma, and this line is going to be set of all x such that my W star transpose x is equal to minus gamma.
Ma'am,
Hmm.
if like W star transpose Xi is greater than or equal to gamma, then minus of star transpose Xi should be greater than or equal to minus gamma. It's like
No,
the
why
sign,
is that?
that sign should change, no? It should be less than or equal to gamma.
You
You
see,
multiply with minus. Like,
see this what is the linear separability condition? So it says W star transpose xi yi has to be greater than equal to gamma, right? And like we showed both the cases where my yi is plus 1 and where yi is minus 1. When yi is plus 1, this is okay. Okay.
okay, okay.
yi is minus 1, you have this minus of W star transpose xi to be greater than equal to gamma. Now I can take the minus on the other side and the sign changes. So my W star transpose xi has to be less than equal to gamma. So this is basically giving you this side of the um this portion, right? And this equation is giving you all the points on this side. This fine?
Yes, ma'am. Uh, Ma'am, so what I have understood that
Hmm.
we don't want my xi to lie on a W transpose explain line. So we are predicting a line that is W star xi. So all the xi will lie on that line or beyond that line.
No. So they can lie, if you look at this data point, I mean, they need not be exactly lying on this margin, right? I mean, they can be. That's why I have like marked these regions. So
Yes,
this
ma'am.
whole region you can
Minimum that
have,
line and beyond that line.
yes. So you can have all the positive point on this direction, and you can have all the negative points on this side. So it may not exactly be lying on the margin that we have drawn. It is beyond the margin. You have all this data set. Okay.
Yes, ma'am. Okay, ma'am.
So, but exactly on this line, if you see, it will satisfy this condition. It is going to have all those xi such that W star transpose xi is exactly equal to gamma. And on this line, it is exactly equal to minus gamma.
Yes, ma'am. Okay. Thank you, ma'am.
Yes, Kaushik, you have you have any doubt?
Ma'am, basically, yes, I have a doubt. Like, ma'am, basically, we are introducing gamma so that we can reduce our mistake. Like, in for upper one, if we are in that all the data sets are of positive, then we should reduce the negative value in that region. Or
No, see, this gamma has nothing to do with. See, you like this is just an assumption that you're making. Okay, so like initially the assumption that we had made is that the data set should be linearly separable. It means there should exist some W that is generating this like linearly separable data set. So start there is some W which separates my positive from the negative. Okay, but there was a case where my data set would have lied exactly on the distant boundary, and that would also have been correct. But now what we are saying is we are making this additional assumption which says it shouldn't be just linearly separable, it should be linearly separable with some margin. Okay. so that there is some gap between the decision boundary and the data points. Right? That's all. And if we make this assumption, like these are the equations of these margins that we have. So the positive side, it is set of all x's such that w star transpose x is equal to y is equal to gamma. And if you look at the negative side, the equation is basically x set of all x's such that w star transpose xi is equal to minus of gamma. All right. And anything beyond that margin, you have this data set. So on the positive side of the margin, you have the data set with positive labels. On the other side, if you see this side, you have set of all the data point which has the negative labels. I hope this much is clear. Okay.
Yes,
All right. Yeah. So now let's move further. So this is one assumption that has been made. Uh, then the other two assumptions are to prove that uh, this algorithm actually converges. So the second assumption that we have made is called the radius assumption. And what it says is that all the data point that you have, so let's say you have this data set, um, you have this point, you have this point, all that, right? So what we are saying is that there is some r, there is some radius, or say that there is some r which actually closes or which encloses all my data point. Okay, so maybe there is some data point here, and this is this radius r. So all these data points are in this wall of radius r. Okay, so whatever is the, I mean, this wall could be anything. I mean, this wall could have been this one, this wall could have been this one. So the only thing you have to take care is that there is for every data point, so for every I, you have some r. So there is just some r which is positive, okay, such that all this x's, right, all this x's, the length is actually less than equal to r. So r can be anything. It will not be strictly limited to the length or the largest length of the data point. It could be any r greater than or equal to this xi length. Okay, so this is one assumption that we are making. And the third assumption that we are making is that uh, the norm of W star is 1. And this will help us in like when we are proving this perceptron algorithm convergence. Okay.
Ma'am, this the margin, the gamma margin we are keeping, is it because we want to converge the algorithm at the lowest possible steps? Is it the reason? Or
Yeah, so yeah, I mean, we have introduced this gamma margin because we have seen that in extreme cases where the data point was actually lying on the decision boundary, there was a problem with convergence. Those data set was not converging. I mean, those that algorithm was not converging in that case. Okay,
so,
so
so it will
this,
cause trouble in real time.
yes, so this assumption of adding this margin to, I mean, not just linearly separable. I mean, it is linearly separable with some margin is helping us uh, like I mean, it's helping us in proving it better. Just say.
so ma'am, shouldn't we update the algorithm with this as a margin?
No, I mean, why should you update it using this margin?
Okay, so if the data points,
My algorithm still stays the same. My update rule still stays the same, that WL plus 1 is WL plus XIYI.
okay, so we don't do anything with the data points in the margin.
No, no, I mean, see, this is just an assumption, right? And Assumption as in like how the data set has been generated. So the data set which are linearly separable with some margin, if you run the perceptron on that, it will always converge. That's all it says, right?
Yeah.
And this is the update rule for the perceptron. Okay. So I think if we do the proof, it might take a lot of time. Okay, let's see. I think we can quickly do it. So what we have to prove here is that, so what we want to prove, we want to prove that perceptron algorithm converges. We want to prove this. So let's say um, for at some time step uh, there is a mistake with my data point x comma y. All right. So if WL is my current guess, this is my current guess, then I will make the update because the mistake is happening with respect to this data point. Okay. So if we do the update, your WL plus 1 should be equal to WL plus XY. This is fine. Now we want to see that uh, how does the length grow when we do this update. So if you look at the length of this WL plus 1, so what it should be, so this is WL plus XY norm square, and this is just a vector, and we can write this as WL plus XY transpose times WL plus XY, right? And if you just walk around, it will be WL transpose. So WL transpose plus XY transpose. So it can be written as Y transpose X transpose times this WL plus XY. So this is what? This is WL transpose WL, which is nothing but WL norm square plus WL transpose XY plus YX transpose WL plus YX transpose XY. Fine. Just look at the last part here. So Y is our scalar. So we can write this as Y X transpose X, which is nothing but
Norm squared of it.
yeah. So this is norm X square X, and this is Y. If what happens if we leave the Y here, so it will be Y transpose X transpose XY. Yeah, so Y transpose Y can be written as norm of Y square. So, but that is nothing but 1. So this is fine. Okay. This is fine. This is also okay. Now, these two terms are actually the same thing. So, we can write this as 2 times WL transpose X Y. So, overall, how does the length of WL changes? So, length of WL plus 1 now is length of WL plus WL transpose This is fine. Now what do we know about this? We have made three assumptions. One is linear separability with gamma margin. One is radius assumption, and one is the length of my weight vectors. So what can we say from this norm of x square? Can you do something over here? Anyone? Any guesses? What should we do here? No? See, we know that from the radius assumption, all my data point should be enclosed in a circle or in a ball of radius r. So we know that norm of x square should always be less than equal to this r square, right? So this can be written as norm of WL square plus 2 times WL transpose XY plus R square. This fine?
Yes, ma'am.
Okay. Now, see, this, I mean, this WL was making mistake for my data point x comma y. So if it was making a mistake, it means that my WL transpose x, the length and y, their sign should have been different. That's why it's making a mistake.
Yes,
So
ma'am.
this should always be less than equal to 0, right? So this term will always be positive. That is WL square, norm square, plus R square, right? Because the previous term, this term, is always going to be smaller than this term because of this second quantity we have. Because with respect to the current W, which is WL, it is making a mistake for XY. So this is always going to be a negative quantity. And if this is going to be a negative quantity, if we remove this point, if we remove this term here, I mean, you will bound this with WL square plus R square, right? This is okay? Everyone gets this? Okay. So what did we get here? Or what we get here is my WL plus 1 norm square is less than equal to WL square plus R square. So now we can recursively use this formula, and what do we get? We'll get now WL square should be less than equal to WL minus 1 square plus R square plus R square. This is less than, now this becomes 2R square. Okay, this becomes 2R square. And now again I can use this formula on this. So what happens? WL minus 2 norm square plus R square plus 2R square, which is norm of WL minus 2 norm square plus 3R square. So you can keep on repeating this. Okay. And what do we get? We get at the end, we'll have WL minus L, which is W naught square plus L plus 1 R square. This okay?
Ma'am, LR square only, I think.
LR square, so no, right? L plus 1 R square, because you have
Professor used
your,
LR square.
no, what is this going to be? This is nothing but WL minus L norm square plus uh, L plus 1 R square, right? Because if you have 2 here, see if you have 2 here, this is 2 plus 1. So if you have L here, it should be L plus 1. Make sense? You already
Yeah.
have R square over here. Now you are doing it L, subtracting L terms from L times you are doing it. So you have L plus 1 coming here. So what we get is, we get norm of WL plus 1 square has to be less than equal to norm of W naught square plus L plus 1 R square. Okay. And norm of W square, like from my third assumption that we have made, this has to be equal to 1, right? Because we have assumed uh, that the length of W star has to be 1. So that should be,
Hello, ma'am.
sorry, W naught has to be 0, not 1, sorry, 0.
Uh,
Because this is our initial assumption. So what we get is WL plus 1 square has to be less than equal to L plus 1 R square.
Ma'am, it is L R square, madam.
It is
ma'am,
L R square.
ma'am, we are
Yes.
taking WL plus R square, no, ma'am. So we can subtract maximum L from WL, no, ma'am, for WL plus 1. Uh, can you scroll little it up?
Mhm.
Uh, yes, ma'am. The equation is WL plus 1 square is should be less than equal to WL square. So maximum we can subtract from WL should be L, not L plus 1, no, ma'am. The line
Maximum
where
it
we
has
have double checked that.
maximum it is L mistake.
Um, wait. So WL plus 1 square has to be less than equal to WL square plus R square. This is
Yes,
okay.
ma'am. So, ma'am,
This
we can't subtract WL. We can't subtract L by L plus 1. We can subtract only L, ma'am. No.
we have subtracted only till L, no?
But we have taken L plus 1.
Because L plus 1 you are getting. I mean, see, WL plus 1 norm square is less than equal to WL square plus R square. When
Okay.
we again apply on this, we get WL plus 1, WL minus 1 square plus R square, which is nothing but norm of WL minus 1 square plus 2R square.
Uh, okay,
This way.
ma'am.
Now,
But,
if we
ma'am,
do it again, it is WL minus 2 plus 3R square. Right? So, at the end, you are going to get L plus 1, no? Because you already have an R square from here. And
Ma'am,
you are,
please check once
but in
lecture
lecture,
slide.
sir has told us that there will be L R square.
uh, okay, but um,
What you are saying is correct, ma'am. But sir has told us that there will be LR.
yeah, okay. Yeah, I remember there. I remember that. But if you see, like, it cannot be L, no? I mean, if you're subtracting L from there, you're reaching till W naught, it has to be L plus 1.
Yes, ma'am. Ma'am, what you are saying is completely correct. But
Hmm.
okay,
Yes, it doesn't matter actually. See, it doesn't matter. Okay, I'll tell you why at the end. So all we have done is that how many mistakes has been done. Okay, we started with W0, then we went to W1, we went to W2, and that's how we are reaching till WL, right? So when we are saying WL is making a mistake, we have already made L plus 1 mistake, right? So all it says is there are the number of mistakes that we have made is L plus 1. Okay. I will tell you why this L and L plus 1 does not matter. Like if you repeat this, I mean, like now all we got is WL plus 1 norm square is less than equal to L plus 1 R square. Okay. And it's correct. So you will get L plus 1 R square. All right. Now what we want is, currently what we have is an upper bound. So what we also want is a lower bound to it. All right. So to get the lower bound, now let's say we want to see, so this WL plus 1 transpose, when it acts on this optimal W star, this W star that linearly separates my data set, then how does it, um, like what happens after that, right? So what did we have here? We had WL plus XY transpose W star, okay? And this will become WL transpose W star plus Y transpose X transpose W star. That's fine. So this can be written as, so you have WL transpose W star plus W star transpose X is also what we can write times Y. And now since this W star is linearly separating my data set with gamma margin, then it has to be greater than equal to gamma according to the definition. So your WL plus 1 transpose W star, when you do, you get WL transpose W star. So this has to be greater than equal to gamma. Okay. So now again you repeat the same process. So what you get? Now this term is going to be WL minus 1 transpose W star plus gamma, right? And this is going to be WL minus 1 transpose W star plus 2 gamma. We keep on repeating this and we will reach W naught transpose W star plus L plus 1 gamma. Not L plus 1, L gamma. Okay. So what we have is WL plus 1 transpose W star has to be greater than equal to W naught transpose W star. So again W naught, what we have taken is 0. So this term is going to be 0 and we'll be left with L plus 1 gamma. So we still have to come here, that is come to the point where we have to find the lower bound for length of WL plus 1. What we have currently is WL plus 1 transpose W star is L plus 1 times gamma. So here we use a Cauchy-Schwarz inequality, which actually says that if you have two vectors X and Y, then X transpose Y square should be less than equal to norm of X square plus norm of Y square. So this is called Cauchy-Schwarz inequality, and we will use this to get the lower bound. Okay, so now let's see. So what we have is L plus 1 gamma. So we're looking at the same. So L plus 1 gamma is less than equal to WL plus 1 transpose W star. Okay. Now let's square both sides. So what do you get? You get L plus 1 square gamma square. And if you do the square on this side, you have WL plus 1 transpose, WL plus 1 transpose, uh, W star square, right? So squaring these means what? The vector. So WL plus 1 transpose we will do W star. Oh, sorry. So now this is a place where you can use Cauchy Schwarz, right? So using the Cauchy Schwarz inequality, you can see that my X transpose Y square, it is actually of the form WL plus 1 transpose W star. So we have a vector WL plus 1 and we have a vector W star. So using Cauchy Schwarz inequality, we can do this. So we have WL plus 1 norm square plus norm of W square. And this length we had assumed it to be 1. So what we got is that L plus 1 square gamma square has to be less than equal to norm of WL plus 1 square. Okay. So we got a lower bound for my WL plus 1 square. And what is the upper bound that we have gotten? So that was L plus 1 R square. That was L plus 1 R square. Okay. So from here, what we can say? We can say that my L plus 1 square, gamma square, has to be less than equal to L plus 1 R square, which is equivalent to my L plus 1 is less than equal to R square by gamma square. And what was L plus 1 here? L plus 1 was the number of mistakes the algorithm makes. Number of mistakes the algorithm makes. So the number of mistakes, the number of mistakes that this perceptron algorithm makes is bounded above, is always bounded above by this R square by gamma square. So and what is this R square? R square, remember that R square was basically the radius of the bowl on which in which all your data points was there, right? So that was R square is the bound for a data point, and gamma is the margin for your data set. So the number of mistakes that your algorithm makes is always going to be R square by gamma square. And this is called the radius margin bound. So remember, R was the radius and gamma was the margin. So this bound that you get on the number of mistakes is called the radius margin bound. Okay.
Madam, that R is the radius of circle formed by the two separating line, which is margin of safety gamma. Now,
Uh,
gamma is distance
no.
between those two lines.
R is the radius. R is the circle or R is the bowl in which all your data points are there.
What I'm trying to understand is which is the bigger one.
Which is the bigger one? See here, it's not about like we cannot say for sure that what can be bigger one. No, I mean if your data set, if your x's length are quite small, and maybe you took R to be a value which is equal to the largest length of the data point, then R is going to be small and it's a gamma margin which is positive. So depending on what the length of the largest data point is, I mean, we cannot say for sure that which one is bigger and which one is smaller here. So all we can conclude is that the number of mistakes that my algorithm can make is at most this quantity, which is a positive quantity. That's all I can say. I mean, this can never be negative because R is the radius, gamma is the radius, and you're just squaring it. So This is a positive quantity, right?
So,
And number of
ga-
mistakes the algorithm can make is bounded by some positive quantity. So number of mistakes is bounded. So if this
so
is bounded, I can say it is converging. Yeah,
that gamma is in reality it is some distance, so it can never be negative.
yes, it can never
And
be negative.
and then, ma'am, for any data scenario,
Mhm.
what should be the value of gamma? Like how we decide what is the gamma? Like what, or is it some algorithm decide some static value? Like how we decide what is the right gamma for this data?
No, no, I mean, we don't decide what is the right gamma for this data set. So, I mean, this is the assumption on the data set. Like, whatever data set you have, I mean, it is not just linearly separable, but it is separable with a margin. I mean, there is some distance between the design boundary and the data set. So we cannot say that, okay, this is the margin that we are going to fix. It's not like that. I mean, the margin is already there in the data set.
But can't we know what is that margin, or we don't need to know? I mean,
We don't need to know what we don't need to know what exactly is that margin. What exactly is the value of the margin?
okay, okay.
Okay. So from here saying that which I mean whether R is bigger than gamma or gamma is bigger than R, it's not possible. I mean, uh, these are just few assumptions that we had made on my data set, where we said that R is the radius of the board where all my data set is enclosed, and gamma is the margin through which um gamma is the margin of this between the distant boundary and my data set. So which one is bigger is doesn't matter here. So all like coming to this point where we are seeing that the number of mistakes algorithm makes is bounded by some positive quantity. Okay, so this is bounded by some positive quantity, and that concludes that the perceptron algorithm is converging. So if something is bounded, it converges. All right. So if you're not able to get why because it's bounded, it's converging, it's are you able to understand it? Like if this is bounded, this will converge. Okay, just understand that. See, the number of mistakes that your algorithm can make is always bounded by some number. I mean, it cannot exceed us this number that we have written, this quantity that we have written, R square by gamma square. So it is always within that. So all the numbers that we get that the mistakes my algorithm makes is going to be always lesser than equal to this. So there is some bound over there, and it's going to get repeated, and that's how we can say that my perceptron algorithm always converges. Okay. Any doubt in the proof?
There are many concept later phases. It will be built on this perceptron. How deep we need to understand this concept?
Um, Sorry, I didn't get the last point. You said there
No,
will many.
ma'am, I'm not really sure, but I heard this term in the deep learning or reinforcement learning. This actually resurfaces, though I have not studied those papers. So how far we have to understand the algorithm, the whatever the proof you have done, how far you have to understand this, what depth you have to understand this.
Okay, so um, see, the proof was done to show you that the perceptron algorithm always converges. Okay, and for sure, like whatever we are starting, like whatever we have started in perceptron, we are going to build up more on that. Like we'll see this SVM algorithm, we'll see soft margin SVM, we'll see all that. And for that, it's important to understand this perceptron algorithm for sure. But very advanced topics which are done in deep learning, maybe to that extent you don't need to know right now. Like when you go to active deep learning course, again you will go through you will see the perceptron algorithm, maybe in a different context, in to a different point of view. But for this course right now, like whatever has been done, if you understand that much well, you can easily able to understand what is done in the consequent weeks.
Okay, ma'am. Yeah, okay.
So from this proof, all you have to take is the number of mistakes that the perceptron algorithm can make is always bounded by this R square by gamma square. Okay, that's all. So that was about the perceptron algorithm. Now we can move forward and we'll see what is the logistic regression. So the other classification technique that we're going to see is logistic regression. So
Ma'am, excuse me, ma'am.
yes,
Ma'am, will you be not taking any like example, numerical example for that algorithm, perceptron? Because there
uh,
are some questions on
okay,
that.
you want to do a question? Okay, like we'll be doing this in the next class. Okay, maybe I can do one question. Just 1 minute. No. So I will take something from the practice assignment. Okay. So this is a question from your practice assignment. The data set that we have with us is 0, 2. The label is +1. Then the next data point that we have is 0, -2 with label +1. And the third data point that we have with us is -2, 1. -2, 1 with label -1. Okay. So the perceptron algorithm is applied on this data set, and the initial weight vector is set to be 0. So W naught is 0. Um, um, now what we have to check is what is the W that you get when the algorithm converges? What W will satisfy that? So first, let's write what is W. What is update rule? So update rule is WT plus 1 is equal to WT times X5. So we are saying W naught is set to be 0, 0. Okay. Let's plot this data point just for our convenience. So 0, 2, maybe this is my 1, this is my 2, 0, 2. Oh, no, sorry. So this is my 0, 2. The label is +1, so I'm marking it with blue. Then there is 0, -2. So this is my 0, -2. The label is again +1, and let's do the negative label point with red pen. So you have -2 and 1. So you have a point over here which is -2, 1, and the label is negative. So if you look at this points, and what is my initial weight vector? It is 0, 0. Sorry, I mean this is 0, 0, right? This is my 0, 0. So I pick a point. Let's say I start with the first point. Let's call it point 1. Let's call it point 2. Let's call it point 3. Okay. So I pick a point 1, and now what do we have to check? We have to check with respect to this initial weight vector that we have. So the initial weight vector that we have is W naught to be 0, 0. So I want to check W naught transpose Xi. Sign of this, I want to check sign of W naught transpose X2, and I want to check sign of W naught transpose X3. So if we do W naught transpose X1, this is going to be 0. So the sign is positive. This is going to be 0. This is going to be 0, right? So if all three are 0, the first point will be predicted correct. The second point will also be predicted correct. But there is a mistake with respect to the third point, right? Because here the true label is -1, but it's predicted to be +1. So there is this error, or there is this mistake with respect to the third point. So now because it's making mistake with respect to the third point, I go there and now I do my update rule. So what is update rule? I will do W1 to be W naught plus XY, X3 by 3, right? W naught is 0, 0. What is X3? It is -2, 1, -2, 1, and what is the Y3? It is -1. So this is minus here, and it becomes 2, -1. So my W1 is now 2, -1. So this is 2, and this is -1. So this is my new weight vector that we got. So if this is a new weight vector, I can see that this will again make the mistake with respect to my first point. This is predicted correct. This is predicted correct, but it is making mistake with the first point that we have. So now we go to our first point, and I will do my update. So W2 now becomes W1 plus X2 Y2. So what is the W1? W1 is 2 minus 1. And what is X2? Oh, sorry, it was X1 by 1. X1 by 1. So what is X1? It is 0, 2. 0, 2, and y is 1. So this becomes 2. 2 minus 1 is 1. So we have 2, 1. So now,
Excuse me, ma'am.
yes.
Ma'am, basically, ma'am, when we are taking the W1 in the graph, then
Hmm?
it's making the mistake for 0 minus 2, na?
No, it's making the mistake with 0, 2, no? Because on this side, you are predicted to be positive. This is my W. My
Okay, okay.
W1
Got it,
comes
ma'am.
out to be 2 minus 1. This is my 2 minus 1.
Okay, okay. Got it, ma'am. Got
Now
it.
on this side, you have the positive, and on this side it should be negative. But 0, 2 is on the wrong side. So it is making a mistake with respect to this point. So
Ma'am,
now
we
the
can
new
also
W that
check
we get.
by
Hmm?
sorry, ma'am, we can also check by taking their dot product, and then we can verify like if it's uh, like if the W
Yeah, yeah.
transpose
So
X is.
instead of the figure that I drew, you can also do this. You can do uh now you check what is the sign of W1 transpose X1, what is the sign of W1 transpose X2, what is the sign of W1 transpose X3, right? So W1 is 0, 2. So you have 2 minus 1, you have 0, 2. So this is what? 0 minus 2. So this is minus 2. And the second point, so this is 2 minus 1, and 0 minus 2 is the point. So 0 minus 2. So this is 2. So this is fine because the actual true label was positive and it is fine. If you look at the third point, this is 2 minus 1 and third point is minus 2, 1. So minus 2, 1 if we do, this is going to be minus 4, minus 1 which is minus 5. So it is, the sign is going to be negative. So this is also fine, but this is not correct. So from here I can see, with respect to the first point, my new weight that we obtained, which is W1, is making a mistake. So now I have to do the update with respect to this point x1 comma y1. When we did that update, we got the new weight to be 2 comma 1. So now let's we can do this. I mean, we can follow the same process, but let's see from the graph. So now if we have 2 comma 1, so this is my 2 and this is my 1 here. So now this is my new weight. And now with respect to this new weight, I can see it will make mistake for the third point, for the second point, right? So I will have to do the update with respect to the second point. So it is going my W3, which is going to be W2 plus X2 Y2. And now what is my W2? W2 is 2 comma 1, 2 comma 1, and X2 was 0 minus 2, Y2 was plus 1. I hope it's correct. So 0 minus 2, 1. Okay. So 2 plus 0 is 2, 1 minus 2 is minus 1. So my new weight is 2 comma minus 1, which is coming out to be same as what we first received, what my W1 came out to be. So again, if we do the update, I mean, if we use this weight, again, I will see it is making a mistake with respect to my first point. Again, it will make mistake in the second point and so on, right? So it is going on the loop, right? So I can say from here, since it's not since we are not able to reach to a W that correctly classifies my data point, I can say that um, here the algorithm does not converge. Okay.
So, ma'am, if we have got some new value, then again we have to
We had
like do
to
the
proceed.
procedure
Yeah.
again.
Again, you proceed. You draw on this graph and see what is the W. Like the problem with doing the graph is that maybe if you're not using the appropriate scales, then you might end up getting the wrong thing. So it's safer to go using the sign, I would say. But if you're drawing the graph, draw it appropriately so that you can understand that whatever you're drawing is making sense.
Ma'am, this perceptron, the problem what you did, and does it have any correlation with the gradient descent? Like there also we do check that whether we are going in the uh, descent or like gradient descent or ascent side, and with the learning rate, whether we are moving in the right direction.
Yeah. It has a relation with the perceptron. Actually, has a relation with the green descent. That's a very good catch here. So it does have like it the update tool that you are seeing over here for perceptron. It is very much similar to the gradient descent algorithm that we have seen. So when we look at the loss function of this perceptron, and we try to use like when we do the update, it actually resembles this gradient descent. Yes, Kevin.
Like, ma'am, if it converges, how do we know how many iterations we have to do?
So if it converges, let's say we reach to we reach a W that is correctly classifying all my data point, then to know how many iterations it took, so we can count here, right? So we can, if you look at, so we started from W naught, then till here is my first iteration. Then from W1 to W2 we go. It's my second iteration. W2 to W3, it's my third iteration. Let's say here, uh, let's say this W was a W that actually classifies my data point. It means I got this W, then what do? I check the sign of this W3 transpose X1. I check the sign with W3 transpose X2 and W3 transpose X3, right? And if it all satisfies, I can say that my algorithm has converged in 3 iterations. Is this okay? Okay. All right. So we did one question. So in this question, like my algorithm is not converging, but maybe you will come while doing the assignments, you will come across certain questions where you will see um, you are getting some W where it actually converges. Okay. But if you get a question, you should know how to do this. The process is the same. Okay. Now let's move to the next classification algorithm, which is logistic regression. So in logistic regression, like let's see. So in perceptron, what we did is we said if my W transpose X was coming out to be greater than equal to 0, uh, we predicted Y to be 1, right? And if it was less than 0, we said it is -1 or 0. Okay. But what if we relax this assumption that we made? Whatever linear separability assumption we made, what if we relax it? So instead of like just going this with the strict value that is Y is equal to 1 or 0, what if we assign some probabilities to it? Like if we have a W which is, I mean, if we have a data set which is not linearly, and if we have a W which is not linearly separating my data set, let's say we have all the positives here, and there is one negative point here. There can be some positive, one negative point here. Then you have negative, 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 some positive point. So, I mean, you won't have any W which will linearly separate this data set, right? So, and that should also be the case that um, if you have a point which lies more far, like which is this is the margin we have, the points which are very far from this distant boundary that we have, we should have more confidence in that point, saying that this will have a positive class, it will belong to a positive class, right? And than the point which is very close to my distant boundary, because it is quite possible that the points which are closer to my distant boundary, they can be from a negative class. But can we assign some sort of probability to it that okay, maybe we can say with more confidence that if the points are farther away from the farther away from this side, I can say with more confidence that this point has a positive label, or the points which are here more closer to this boundary, they are belongs to the positive class, but with lesser probability. So some kind of probability is what we want to assign on this case. So we are not going with the linear supplementary assumption, so we are relaxing it, and we are saying, let's say all the data point can have the possibility that it can be coming from a positive class or it can be coming from a negative class. So for that, we are giving a metric which is the score, and the score will define as Z is equal to W transpose X. Okay, so this is how we are defining the score. So what we're saying is the larger this value is, so the larger this Z is, the higher the probability of this point being labeled as +1. Okay, so and one of the function that actually satisfies this is this sigmoid function. So if we have the score on this x-axis, and if we plot the sigmoid function, so sigma of z, and we want to associate the probabilities here, right? So it should bound between 0 to 1, and this sigmoid function, how it looks like is it kind of form an S shape here. It's not exactly converging here. I mean, it should be something like this. All right. So as my z tends to infinity, so as when we say as z tends to infinity, it means higher your score is, higher the chance of this point being labeled as +1, right? Because this is the highest here, right? You can see that. And as z tends to minus infinity, the lower the chance of this point being labeled as +1. Okay, so this sigmoid function, or we also call it a logistic function, it kind of aligns with what we want here. So the way this function is defined, so this g of z is this, and this is my sigmoid function or the logistic function. The way we define is g of z is 1 upon 1 plus e to the power minus z. So what what we are saying is the higher the score you get, the more chance of this point being labeled as +1. So okay, so this is okay. Any so far before I proceed further. Okay. So what is happening is now the way we have designed this, any W will work for my data set, right? If the data set that you're seeing over here on this page, any W should work now, right? So because now we are not strictly saying that if it fell on if it falls on one side, it's all labeled as +1, otherwise labeled as -1. Now it doesn't work like that. Now we have assigned a probability, and each of these point has some chance of this be coming from a positive class or the point being coming from a negative class. Okay, so any W is possible. We can have any W for such kind of data set. But now, what is that one W which gives us the least error is what our goal is now, right? So now that is we have to find out. So we have the W. I mean, we have various Ws possible, but what is that W that will give us the least error, or that will give us the least misclassification? So we'll see how to get that. So the data set that we have is my xi comma yi, where I is varying from 1 to n. And what we know is that um, given x, right, the probability that it is coming from label 1, it is a label 1, is given by this sigmoid function g of z, which is given by 1 upon 1 plus e to the power minus z, and z was nothing but w transpose x. So it was a score, right? So 1 plus e to the power minus w transpose x. So this is what we know. So what we want is we want to estimate this w now. Okay. So again, we want to know what this w is. So what can we use here? We want to find the w, right? So what can we do here? Again, this is an estimation problem. No. So we want to estimate W here. So what do we know? Like, what are techniques we know through which we can estimate our W?
Mainly,
ML estimation, right? And for ML estimate, um, what is the first thing we need? We need the likelihood. Mm. Are you able to understand? Is there any issue? No? Okay, so what we can do is we can stop here today. Maybe in the Friday class, we can start from this part if it's okay with you. Will that work if we do it on Friday?
yes, ma'am.
Yeah. So by then, if you have not yet studied this part, it will be good if you go through it. And when we see in the Friday class, maybe it is more clear to you. Okay, so we can stop here. Um, and whatever we have not been able to do today, we'll see on Friday session. Okay. All right. All right then. Thank you everyone. We'll meet on Friday then. Okay.
Thank
Bye.
you, ma'am. Good night.